Okay. SolidWorks. Okay. Close SolidWorks. Don't save for now. Let me see. Share the screen. There you go. All right. Now, let me record this session. I'm going to, where is the record? Yeah, there you go.
This meeting is being recorded.
All right. As I said, in chapter 3, we are going to look at what is called adaptive meshing and also meshing technique in SolidWorks. Remember from last time, I mentioned the default type of element in SolidWorks is a TET second order element. Let's see what is the TET element. If you look at this picture, or the other one, the top one, this is the shape of the element when you are selecting a solid element. If your part is solid, the default is TET element. TET element can be first order or can be second order. Or as I said in SolidWorks, it says draft and high quality. Now, what's happening is, if you look at what's happening in terms of the quality of meshing, if you use first order, and if you look at this example here, see, for example, if you have some sort of half a circle or curvilinear path, then there is no way that between two elements you can have a curve. All you have is a straight edge. Meaning that if you use first order, all the faces and all the edges will remain straight after deformation and meshing or mapping. Then this is what's going to happen. Then size can be changed, it can be stretched, it can be compressed, but the shape, it's going to be as the original one, and there is no deformation in terms of edges and faces. When you use second order, which is the default one, then we look at this picture. What's happening here is those edges, which is represents any of those edges here, or even the face, this face, the other face, those faces can be deformed to map say curvilinear path. Then definitely that one is more smooth, more realistic. Then we have two options, and obviously this one is the choice. But this one is available for some specific application, especially when you're dealing with a complicated part or assembly, and there are lots of parts, and you want to apply to make sure that the processing time that you have, or your hardware or software, the combination of hardware and software is going to work properly in terms of processing time, and your computer is not going to crash, and you prefer to use that one. In some cases, even it doesn't matter which one, the result is a bit independent from, slightly, we can say slightly independent from the first order or second order elements. Anyhow, as we mentioned last time, if you remember, we said that we can apply different size of element as well. And when we say size, and we are talking about TET elements, that's a TET element here. Now, size means that for a TET element, if you draw a sphere around that TET element, the diameter of the sphere represents the size of that element. Okay, when we say, for example, 4 millimeter, it means that TET element you can fit that TET element before mapping and deformation. Standard TET elements in a sphere, which is the diameter of the sphere is 4. And when you have the part, as you see here, and you are applying mesh, or you're mapping the mesh into the part, then as you see here, those area which you have a rapid change in terms of geometry. For example, here you have rapid change in terms of material. There is material here, for example, from here all the way to here is homogeneous somehow in terms of the shape and in terms of the distribution. But when you come to this corner, you have a rapid change in terms of material, and there is no material after that. Then SolidWorks is trying to map the mesh such that it's going to stretch, or it's going to change the form of the, shape of the size of this element such that it's going to cover those corners, which is you have rapid change. Now the question is the quality of mapping those corners, or in general entire part by meshing, is called mesh quality, because if you increase the size of element, if you change the type of element, definitely you will end up with better, or if you go to the second order, better quality. First order, say coarse size, you definitely will end up with low quality. Then we should have some sort of, it seems that we should have some sort of indicator for mesh quality in SolidWorks or any meshing tool. Now what we have two clear indicator or metrics to measure the mesh quality. The first one is aspect ratio, and the second one is Jacobian ratio. Aspect ratio is clear. You have ideal shape of that element, and we call that one aspect ratio equals 1. All the sides are equal, all the faces are equal. Then after mapping and after applying force, you may end up with those kinds of elements. These elements is going to be some sort of aspect ratio, won't be 1 anymore. It can be a stretch, for example, in one direction. All right, and we have to define what is called aspect ratio to show what is the ratio of say the deformation, or what is the magnitude of change in terms of the size of shape of that elements. That this is one. And the second one is Jacobian ratio. It's a little bit concept is not clear, but what I can say here is not clear without dealing with math. This is what I'm saying. What's happening, for example, if you look at this element, somehow the deformation or mapping is such that you see those kinds of scenarios. See, suddenly the shape is significantly changed compared to what you had before. Here what the before mapping and loading. Here what you have after mapping and loading. And what it says here, it says the solid, this definition comes from SolidWorks. It says the Jacobian ratio is a measure of the curvature of edges and distortion at the mid-side node when the second order TET element is used. The second order, which is you have node in the middle of each edge, then what's going to happen is the distortion is such that you have curvature. It means that you don't have any line anymore, or and what you have, that line is going to be distortion is such that you cannot identify it as a line anymore, and it's going to completely dislocate from the original shape, and we call that one Jacobian ratio. I'm not that much sensitive on this one because you can't do anything on in terms of this one, and it's typically what we have. I think I put the number. No, number is in the textbook. If you look at the number, in most of the cases that we do, Jacobian ratio is not is acceptable. It's supposed to be lower than 40, I think, something like that. Then check the number, please. But then what's going to happen is that is we are on the safe side. But what's happening here is that aspect ratio, which is a good indicator of indication of the quality of your mesh. As I mentioned before, we have coarse, default, and fine mesh. We showed you that if you have a part, you can mesh it. I'm not talking about running the simulation, just meshing technique, just mesh itself. And you can change the magnitude of that TET element, the size of that TET element. Also, what the interesting thing is we have some sort of reporting mechanism in SolidWorks to get some sort of information about aspect ratio, the number of elements, the number of nodes, and so on. Let me show that one in SolidWorks. If I go here and open, where was the part now? Let's go to share file, select folder, make the 6. Hopefully we have it here. Yeah, it's here. There you go. See, this is a part, okay? And as you see, we can say, go to this fillet and suppress them. We don't need them really to, those are not critical in terms of our design. Definitely we need to have one here, but I'm not going to, I'm just going to focus on that one shouldn't, if there is a fillet here, this fillet shouldn't be suppressed, because this is if you apply force, that is the sharp corner that if you apply fillet is going to change the stress concentration or improve the stress concentration significantly. But any fillet chamfer here around the part, you can easily ignore them. Now, but since I'm going to just focus on meshing, I'm not going to apply load, then I'm not worried about what's going to happen here in terms of the stress. Now, let's create a simulation. And let me, I don't know, that's a fixed geometry here. I'm not going to even apply force. And material, let's go and change that one to whatever is the default. Alloy still apply, go ahead. Now, I'm going to go to mesh and say create mesh. And what I'm going to do here is I'm going to go to course and apply. All right. Now, if I right click here, see, if I right click here, it says details. This one, it's in your textbook as well. Yeah, you can look at the textbook and find those kinds of information. But here is, if you go to detail, you get a report from mesh. Here is, let's see what it says. It says the name of the study is a static one. Yeah. Mesh type is solid mesh. Mesher use is a standard mesh. We'll talk about that one. What is this? But you can find that one here as well. Automatic transition is type of meshing. We're going to talk about it. We didn't, we didn't apply it here. There is a Jacobian here, 16 points, and also there is a number of nodes. The total nodes that we have here is at max 20,000 something, and the total elements, total nodes is 3,000. Total elements is 1,672. See, this is the element, and those are the nodes. But we have node in the middle as well. Don't forget, it's the second order element. It says percentage of elements with aspect ratio smaller than 3. 96.6 are aspect ratio is, which is very good. This is the 96.6% is the aspect ratio is good. But let's see what's happening here. See, look at this area. Just compare this element and this element. See, SolidWorks is trying its best to cover those areas with those elements, because here, see, compare this element with this element. Here is going to put more elements, yeah. But since you selected the course, this is the best SolidWorks can do. All right, this is what we call mesh quality. If I continue and go to mesh and say this time, let's go with fine mesh. Let's see what's going to happen now. See, much better in terms of covering that area, sharp area, or covering that critical area. But still, as you see, that element is different, for example, from this element. Now, if you increase the number of elements, or if you make the size of elements H smaller, definitely you have better quality here. But you know what is the cost? Yeah, the cost is what? You have to have huge processing time. You can go say, how much is the size right now? Let's see. If I go here and look at here, mesh parameter, the size is 5 millimeter, yeah? But you can go to 1 millimeter. You can go to half a millimeter, 0.02 millimeter. But the meshing takes lots of time, and that's not the key issue. The key issue is when you run the simulation, you need to have a wonderful combination of hardware and software to get to have a say reasonable processing time, which is not the case. We have a super duper computer, workstation, and so on. And the question here is, okay, then it seems that if I increase the size, decrease the size of element, I get better result. But on the other side, there is a problem in terms of computer, in terms of processor, and in general, in terms of processing time. I can run this simulation, say, for half a day. If my computer is not going to crash, say half a day with, I don't know, with 0.001 millimeter, those kinds of number, and get a wonderful result, very precise. Now the question is, okay, but I don't have that much time. Then what should I do? Can I go with, say, 5 millimeter? Can I go with 2 millimeter? What is the number that I can trust the result in terms of? Remember last time I said, especially when it goes to a stress result, is sensitive to your mesh refinement. Then the question here is, all right, what is that magic number that I can say, okay, I'm good enough? Not less than 2 millimeter, more than 2 millimeter. I don't want to see it. It's not something that I'm interested in. It's not going to really change my design in terms of the result. Then that magic number is a critical issue when it goes to mesh refinement. Mesh refinement means that you're going to refine the mesh, you're going to decrease the size, or you're going to increase the number of elements. Let's back here to my PowerPoint. Now, as you see, I think I mentioned that one. If you do mesh refinement, a stress result is sensitive, but the displacement result is not sensitive. We talked about that one. Now, a couple of rule of thumb is good to know. See, the recommendation is, first of all, the couple of those, remember it said we should have a magic number to somehow help us to say, okay, let's stop at that point and don't try to decrease the size because it takes lots of time. And maybe you don't have a strong infrastructure in terms of hardware to run the simulation if you crazy go about the size of element. We need to end up with some sort of rules. And one rule here is make sure that you have at least 2 to 3 elements to cover the thickness. And to be on the safe side, always we say 3 elements, right? I hope it's clear. See, whenever you have part, the size of element should be such that you have at least 3 elements covering that area. From math perspective, it means that you have enough boundary condition to solve the problem from SolidWorks perspective. But rule of thumb for us is at least 3 elements to cover thickness. However, it doesn't mean that if you have 3 elements, you are okay. That's the start point. Then we need to look at what is called, the terminology that I'm going to use is convergence tests. You need to look at what is called convergence test. But the start point is 2 to 3 elements to cover the thickness. If you don't have it, don't try convergence test. Your simulation is wrong. You need to have enough number of elements to cover the thickness. The second thing here is be careful about what is called concave element. Again, that's another rule of thumb. See, if you look at here, one of those elements, for example, this element, this one, is going to cover 90 degrees. Here is flat, here is flat. And one element is going to take care of all that deformation. And you have huge deformation on that particular element here. This is starting from 0 all the way to 90 degrees. That is not acceptable. We call that, this situation is concave element. And you need to look at those kinds of fillet. If you can, some cases you cannot, as I said, you cannot defeature the fillet. Make sure that it's going to cover at least with 3 elements, which is roughly about 30 degrees each element. But again, if you go with 3 and 3, 30, or 3 elements here and 3 elements here, then that is the start point. Don't forget that it's not, you can't say that is good enough because of sensitivity of stress with size of element. And we have to do what is called convergence test. But that is the start point. Make sure that you do check your thickness, the part thickness in different area and the fillet. Make sure that at least you have that one in the beginning, and then start convergence test. And in order to do that, you have to look at the feature size. What is the minimum feature size that you have in terms of thickness or in terms of fillet? If you have R equals 1 millimeter, which is the fillet is 1 millimeter, and you are going to apply mesh with 1.5 millimeter, then you are not going to have a good result, and maybe wrong result here, because you are here, you have 1 millimeter fillet, that's a drawing, that's a part, and you say my mesh, the element size should be 1.5 millimeter. Then what's going to happen here is one element is going to cover 90 degrees. Same goes here with the thickness. Yeah, if you have the thickness say 2 millimeter and you define 4 millimeter for your element size, then wrong, because we said at least you need to have 3 elements. Then you have to have at least 1 millimeter to cover that area to end up with at least 2 or 3 elements. One more thing is interesting thing tool that we have in SolidWorks is remember last time when I not last time when I went through the tutorial 1 chapter 2 last hour, I had to create 4 studies and to look at the result. There's an interesting tool in SolidWorks which is called Trend Tracker tool. You can run the simulation and then you can run another simulation and just change one parameter, and SolidWorks is going to keep track of the result and compare them. Let me show you this. That's a good one to have. I'm going to look at the trend tracker, and I'm going to look at what is called convergence test. I mentioned a couple of times convergence test. Let's see, what is the convergence test? All right, let me go to SolidWorks one more time. Any question so far? All right. Although I'm going to give you time at the end of 5 minutes before finishing the lecture, so you can ask your question. All right, let me see. Go to SolidWorks. There you go. Let me close this one. I don't want to do this part. That was good for mesh, but I'm going to go with link. And now this is a link. Let me just put this one in a different, save it in a different folder. I don't want to really put that one in the folder that we have lots of studies. I want to have, let's say, save as, and go to desktop. I'm going to create new folder and test FEA. Here. I'm going to put it here. All right. Now, what I'm going to do here is create a new study. And let's go with material. Alloy steel is okay. Let's go and apply force. Let's apply. Okay. Okay, the direction. Let's change the direction. Let's change the direction. And now, see, I'm going to run this simulation first. There you go. Oh, we forgot to add fixture. Come on. Fixture, fixed geometry. Hey, this one is coming up. Don't need advisor. Oh, there you go. And let me close this one. It's not going out. All right. Now I'm going to run this simulation. Okay. What's happening here? All right. Correct. All right. Now, let's see. Where was that? Trend tracker. They move it again. Yeah. Yeah. There you go. See? I don't know. For some reason, I thought it's in the result. I don't know why they put in the static again. Okay. Here is trend tracker, as you see. Now, what's happening? If I select that one, it's going to look at all the result here as a base. Okay. This is just a base. And then if I change any value from now on, it's going to keep in the memory, keep the value in the memory, and I can take a graph from the final result. For example, I'm going to create 4 study now with different mesh size, and I'm going to look at the stress. What's happening to the stress? Remember, I had 4 study, and I had to look at and compare the result, and I have to look at the numbers. Now I'm going to ask SolidWorks to run everything with one simulation, take the first one as a base, and I'm going to repeat 4 times, and SolidWorks is going to give me that graph and compare the result. That's an interesting tool that we have, another interesting tool in SolidWorks. I'm going to go here and say trend tracker, and as you see here, we have trend tracker here now. See, this one is there. I'm going to say this is set the baseline. Okay, now is mass, stress, and those are the baseline that we have. It's going to, as you see, something is happening. It's going to just memorize the result for now. Now, what I'm going to do, I'm going to say, let's go to mesh. I don't want to see. All right, I'm going to say how much was the mesh parameter? Was 7. I'm going to change that one, say to, I don't know, 3. All right, and run it. It takes lots, it takes time to run this simulation, but I'm going to just run maybe a couple of numbers. We don't want to spend time to watching the screen running the simulation. As long as you know what's happening here and what is the procedure, you'll be okay. What I did this time, I changed the mesh size from 7.5 to 3 millimeter. Yeah, and now my computer is solving this problem. Trend tracker with save existing model. Do you wish to continue? Yes, I will continue. All right. Now, just going to memorize those numbers again. And one more time, go. Okay, good. One more time. As you see, still I'm working in one simulation study, yeah? But up to this point, I ran two simulations with 7mm and I think 3mm. Next one, I'm going to run one more, but stop it there. But you can go ahead for yourself and run more simulation and compare them later. Save the time. I'm going to run one more. I'm going to say create a mesh. And this time it was 3. Let's go with, I don't know, 2. Let's see how long does it take. Too much. Too much to ask from computer to run during the lecture. I think we shouldn't go to 3 minutes. But anyhow, let me run this one. And I'm going to back to the lecture note, and you can see the result. This one takes time, but you can continue PowerPoint. And I'm going to say run it. It takes time to run this one. Let's stop sharing and then back to PowerPoint. When that one is done, I'm going to show you. There you go. See, if you do that, this simulation using the, for example, in this case, instead of manually changing them, you can just go with trend tracker. Yeah. If you do that, then SolidWorks is going to show you this graph, something like this. Make it big. Hopefully, my simulation is going to give me results. I can show you this graph. See, what's happening here is from point 1 to point 2 is significant change. See, and then it seems that it's going to be somehow convert to a number. And if you look at the PowerPoint from last week, do I have here convert distance? Yeah, let's see here. See, if you look at here, another part. See, here I could run more simulation. I don't want to spend time. But what's happening here is, see, I can change the element size from 4mm to 2mm to 1mm to 0.5mm to 0.25mm. This one. And then the magnitude of stress, I'm going to draw the magnitude of stress along y-axis. Then what's happening here? You have element size smaller and smaller to the right. I'm going to decrease the size of element. And I'm going to, okay, this is my simulation board. I'm going to show later on when it's continue this PowerPoint. Then what's going to happen here is every time the change from this test to this test, see, from this size to this size, is smaller from this size to this size, is smaller from that size to that size. What is the point here? It seems that, as you see, the convergence is happening. Then maybe 4mm is not a good one for this simulation. The reason is 4mm represents how much? 330 MPa? But let's go to 0.5 millimeter. 0.5 millimeter is 400. Then if I run the simulation with 4mm and say, stop, say this is good enough, then I'm losing about 100 MPa in my result. 100 MPa to in 300 magnitude of stress is huge. We're talking about 30% error, 40% error. But if you continue, for example, when you reach to 0.5 and run 0.25, you see, okay, how much is that? It's 420, 430. Here is roughly 400, say 8. We are talking about 12. 12 is different from 100. 12 divided by 300, we are talking about how much? 3%, 4%. And that is going to help you when you never ever reach the final answer. Because if you know the final answer, what is the purpose of simulation? You don't know, all right? What's happening here is you can continue and reach to the point that it's not, you're almost there. And say, you spend 20 minutes and you say, you know what? I'm going to take care of that, say 3%, 4% error. I see the convergence. I'm not going to continue. I'm going to increase a little bit, maybe factor of safety, and I'm going to start the simulation, stop the simulation. Because simulation is numerical approach. You never ever reach the exact number, but you should stop. And this is what we call convergence test. Hopefully the concept of convergence test is clear. Now I'm going to stop. And any question, let me just stop recording.
The recording has stopped.
Yeah, any question from your side? We have a couple of minutes. Any question related to convergence test?
Hi, Cyrus.
Mm-hmm.
So I'm just wondering, does the convergence test kind of compare the results of like a concave element and try to basically make that ideal?
No, what's happening? Good question. First of all, remember we said we have 4 types of error, and one type of error was discretization error. Yeah.
Yeah.
Convergence test is going to take care of. It's not going to eliminate. It's going to minimize. When you stop, you can see the convergence. You say, okay, I'm going to stop here. It's going to minimize the error related to convergence test, related to discretization error. But other than that, it's your job to take care of any problem related to concave element or thickness. Let's talk about this one, this issue. My suggestion is ask your question, please, in the beginning of our lecture on Wednesday. I'm going to explain, all right? Because we are running out of time, and some students, they have lecture right after this.
Okay, thank you.
Okay, yeah, have a good one. And if you have any question related to convergence test, please ask in the beginning of our lecture on Wednesday. Bye.